Hello. Today we are going to solve a problem on the relativity of mechanical motion. Let's begin. An athlete rides a jet ski at an angle of 35 degrees against the current of a river flowing at a speed of 2.8 tenths of a meter per second. If his speed relative to the ground is 9.5 tenths of a meter per second at an angle of 20 degrees against the current, what is the speed of the jet ski relative to the water? Let's write down the terms of the problem. We will determine the speed of the jet ski. We'll denote it as v1, exactly relative to the water. And we know that there is an angle which we will designate in the figure in 35 degrees. This is respectively the direction of motion of the jet ski in relation to the flow of the river. Then we know that the velocity of the river flow, let's denote it as v2, we know 2.8 tenths meters per second. And it is also known that the velocity relative to the ground of this jet ski, let it be v3, is 9.5 tenths of a meter per second and is directed at an angle, let's write it v, 20 degrees. So, in such situations, we necessarily make a drawing in order to explain how this velocity vector is located, what angles we are talking about, and further, already based on the vector construction, let's see how to solve such a problem. Well, let's draw a river for starters. And let's say that the flow of the river is directed in this direction, its velocity v2. It is known that the jet ski itself moves at an angle of 35 degrees with respect to the x-axis. We will choose the base axis, relative to which these velocity vectors will be oriented. This is the axis perpendicular to the flow. Well, in the classical version of this method of problem solving, we will rely on this very construction. So it is known that the speed of the jet ski itself is directed at an angle of 35 degrees to this axis. This is the velocity v1, which is the velocity of the jet ski relative to the water, and that's what we're going to determine. Further, it is known that the velocity v2 is directed at an angle of 20 degrees to the axis. That is this angle, this is the angle alpha, and relative to the ground, the jet ski moves at a different speed and angle. Why does that happen? Well, the whole point is that the speed of the jet ski relative to the water will be defined as a vector sum of two speeds. These are, in fact, the speed of the jet ski v1 and the speed of the river current v2. We can mathematically write this expression, that is v3 vector. It is the sum of the two vectors v1 and v2. Thus, it turns out, in order to get the total velocity of the jet ski relative to a stationary reference frame, which in this case is the ground, we must add up the two velocities, the natural velocity of the jet ski and the velocity of the river current. Conventionally, we can add this vector to the vector v1. Remembering the triangle rules of addition, we combine the beginning of one vector with the end of the other, and then we connect the beginning of the first vector to the end of the second vector. What we end up with is a triangle with definite sides. The first side, v1, represents the speed of the jet ski relative to the water. The second side, v2, represents the speed of the river current. And finally, the third side, v3, represents the speed of the resultant vector of the jet ski relative to the ground. And that's exactly what it's directed at an angle of beta to this x-axis. This is the vector diagram we have, and from it we will have to determine the value of velocity v3. How do we do it? Let's look at the solution of the problem, in terms of which we can calculate this velocity. Here we can see that there are certain vectors that are located at certain angles to the x-axis. We can also introduce the y-axis if necessary. Let's spell it out as well. So the y-axis. And let's look at how we can work out the issue with the components of vectors on the data. Axes and what components we're likely to need. If we look closely at the problem data, we see that we have a river velocity that is directed exactly along the y-axis in the opposite direction. And this gives us a little hint that we will most likely have to work with this axis. So let's pay attention to the y-axis and see how the components of each vector look like on this axis. So the projection or components of velocity v1 on the y-axis is the opposing cathetus in this triangle. Let's draw it separately. So this is vector v1. And these are our coordinate axes that were perpendicular to the end of this vector, exactly at right angles. This is the angle alpha. So it seems that v1y turns out to be true. So the components along this axis, this will be the opposing cathetus for the given triangle, and it will accordingly be equal to v1 times the sine of the given angle alpha. Similarly, we see that in a triangle with velocity v3 we get a similar construction. Let us draw it. Here in a similar way, but with a different angle beta, we get an opposing cathetus. So v3y is v3 times the sine of the beta angle. Well, and accordingly the velocity v2 is directed simply along this axis, and actually the projection we can simply determine by denoting its sign. Now let's display these vectors on a standard diagram so that we can see how this construction looks like in the end. So the vector v1y is pointing vertically upward. We have vector v2y pointing vertically downward, and accordingly v3y is also pointing vertically upwards. From this we can conclude that if we subtract the velocity of v2 from v1y, we get exactly the same value v3y. That is, decomposing these vectors into components, we get this equation. And further, our task now is to collect all this together and get the answer after solving the equation. So v1y is v1 by sine alpha minus v2. That equals v3 times sin beta. So that's the equation we have. We have one single unknown in this equation, which is v1. So we express it out of this equation and we get v2 plus v3 divided by sine beta divided by sine alpha. So that's our final formula. We substitute the value. So v2 is 2.8 tenths. Plus v3 is 9.5 times the sin of the angle beta, which is the sine of 20 degrees, and divided by the sin of alpha, which is the sine 35 degrees. So the approximate velocity we get is 10.5 meters per second. That is, the speed at which the jet ski moves in relation to the water is known as its relative speed. Generally, this value is quite justified because we can observe that the length of this vector must be greater than the length of the vector already in relation to the ground. Essentially, the jet ski loses speed as it needs to move slightly against the current in order to reduce its drift downstream. This concludes our task, and we look forward to seeing you in our upcoming lessons. Farewell.